All right, let's get into it. Today, we are pulling back the curtain on something we use every single second of every day, but almost never think about: computer networks. We're going to unpack how a simple click on your screen can send a message flying across the entire planet in the blink of an eye. I mean, really stop and think about that for a second. You click a link, and bam! Information from a server that could be thousands of miles away just shows up on your screen. It honestly feels like magic, right? Well, it's not magic, but it is an absolutely fascinating system of technology. So at its most basic, this is all a network really is. You just have a bunch of computers that are linked together. But here's the key. They're not just connected for the fun of it. The whole point is to do two really powerful things: exchange information and share resources. So why do we even bother connecting everything? Well, the big one is communication, obviously. It lets us talk to each other, but it also lets computer processes talk to each other automatically. Then there's resource sharing, which is a huge deal. Instead of every single person needing their own printer, you can just connect to one on the network. And of course, that leads right to the third point. It saves a ton of money. Now, as you can probably guess, not all networks are the same. They can be really, really small, like think about the Bluetooth connection between your phone and your earbuds, or they can be unbelievably massive, like the internet itself, which connects billions of devices. And this variety is super important for how everything gets organized. And this is where we get into a really cool concept: topology. It's a fancy word, but all it really means is the layout, like a map of the network. Do you connect all the computers in one long line, which is called a bus? Or maybe they all plug into one central hub, like a star. Or for something really robust, maybe they're all connected to each other in what's called a mesh. This shape literally determines how information gets from one place to another. So beyond the shape, you've also got the scale. We start small with a PAN, or a personal area network. That's basically just your stuff. Then you scale up to a LAN, a local area network, which might cover your entire office or school campus. Go bigger and you've got a MAN, a metropolitan area network, that can link up different LANs across a whole city. And finally, you get to the big one, the WAN, or wide area network, which can span a country or even the entire globe. Okay, so we've got all these computers, connected in all these different shapes and sizes. But how on earth do they communicate without it just being total chaos? How does a message from your laptop find its way to one specific server out of billions, without just getting lost in all that noise? Well, the answer is something called a protocol. You can think of a protocol as the official language of the network. It's a really strict set of rules that every single device agrees to follow. It's like grammar and etiquette all rolled into one, making sure that when one machine speaks, the other one knows exactly what it's saying. And these protocols, they're really the unsung heroes of the internet. You've probably heard of HTTP. That's the protocol your browser uses. But there are protocols for everything. They set the rules for your apps, they figure out the best route for your data to travel, they handle any errors that pop up, and they even chop up big files into smaller pieces to send them more efficiently. They do it all. Okay, so if your head is spinning a little bit right now, trust me, that is completely normal. We're talking about hosts, routers, all these different kinds of links and cables, tons of applications, and dozens of these protocols, all working together, all at the same time. Yeah, it gets complicated. And that right there is the fundamental challenge of networking. With all these moving parts, how did engineers build a system that actually works reliably? How do you create something as enormous and complex as the internet without the whole thing just collapsing under its own weight? And the answer is such a simple, elegant idea that it's just genius. Layers. Instead of trying to solve one gigantic, impossible problem, we break it down into smaller, much more manageable pieces. And here's the magic of it. Each layer has one very specific job to do. It does its job, and then it just hands the work off to the layer above or below it. Critically, one layer has no idea how the other layers get their jobs done. It doesn't need to know. This separation is what makes the entire system possible. Now, to make sure that one company's layers could talk to another company's layers, the world needed a standard blueprint. And that blueprint is called the OSI Model. You can think of it as the official 7-story instruction manual for how to build a network. What's so cool about this diagram is that it shows you the entire journey. Look at the computer on the left. Your data starts at the very top, at the application, and then it travels down through all 7 layers, getting processed at each step. Then it gets sent across the network, and on the receiving computer on the right, it travels all the way back up the stack until it finally reaches the application over there. So let's actually break down what these layers do. The easiest way to think about it is to split them into two groups. You've got the upper layers, which are all about the software and the apps you actually interact with. And then you have the lower layers, which handle the nitty-gritty details of actually moving bits and bytes from one place to another. So at the very top, layer 7, that's the application layer. It's the front door that your programs, like your web browser, use to access the network. Right below that is layer 6, the presentation layer. Think of this as the universal translator. It makes sure data is in a format that both computers can understand, and it also handles important stuff like encryption. Then layer 5, the session layer, is like a conversation manager. It starts, stops, and manages the connection between the two computers. Now we get down into the engine room. Layer 4, the transport layer, is basically quality control. It makes sure all the pieces of your data get where they're going, safely and in the right order. Layer 3, the network layer, is the GPS for your data. It figures out the best physical path across the internet. Layer 2, the data link layer, packages everything up perfectly for whatever kind of physical connection it's about to use, whether that's Wi-Fi or an Ethernet cable. And finally, layer 1, the physical layer, is what does the actual work of turning all that data into electrical signals, radio waves, or pulses of light. And this right here is the real beauty of the whole system. Let's say you invent some new, super fast Wi-Fi technology tomorrow. Because of this layered model, you only have to change things at the bottom 2 layers. You don't have to rewrite a single line of code for how your web browser works. It lets the internet evolve, piece by piece, without ever having to shut the whole thing down. But that brings up a really interesting final point. This amazing OSI model was designed way back in the 1970s. The internet we actually use today runs on a similar, but much more streamlined model. So that leaves us with a pretty big question. Is this classic blueprint from the 70s still the best way to understand the chaotic, complex, and constantly changing internet we all depend on today? That's a debate that's still very much alive.